All right, well, thanks for that introduction, Mark. Oh, got it. Bump me out. Yeah, thanks for that introduction, Mark. I was going to begin by doing a little bit myself, just to say that my main day job these days is working on one of the instruments, one of the 4 cameras on James Webb, which I think current launch date is about Thanksgiving at the moment. Actually, they just sent around a picture. It's actually out of the hangar in Long Beach, and it's moving towards its ship. So it's actually like physically moving to the launch site, which is very exciting. It's all packaged up at this point. For all the rest of us, I was actually just out in Baltimore last week, the end of last week, doing a launch rehearsal. They have this whole simulator rigged up, and we're rehearsing actually operating the spacecraft. So fingers crossed this will actually go on Thanksgiving, and everything will work. So today, though, what I'm going to talk about is not so much JWST, but what we get from observatories like JWST and Hubble and ground-based observatories, and some probably next generation space telescopes. The idea that, you know, once you've discovered an exoplanet, what do you do next? And I'll say also that it's always, I give this sort of talk to a lot of different audiences, and I always appreciate giving it to astronomy clubs like you guys. I feel like there's a base level of understanding here, like we can all talk about the telescopes we have, that for a general public audience, I have to backtrack a little bit. So this is going to be a little bit higher level, I think, than my normal public talk, but I think you guys will enjoy it. All right, let's see if I can increment my slides. Right, okay, so I wanted to start just for 1 second about this picture of the Milky Way and the idea of what are we actually doing here, right? Because in many ways, astronomy is probably one of, or I'd probably argue, the oldest human science in existence, right? You can imagine even before settled civilization in the Middle East, that people looked up at the sky and asked the fundamental questions we ask in astronomy. Just what is going on up in the sky? How do we understand what's going on up in the sky? And even the ancient Greeks a couple thousand years ago had the idea that there might be other planets like Earth up in the sky. Of course, they didn't have the capability to, you know, drill down on that question any further than, you know, just posing it. But that idea that, you know, there might be other planets, there might be other life somewhere up there has been with us for, you know, thousands of years. And people have been working on it for thousands of years. And we're at a very sort of pivotal moment in that history where we're finally getting very close to being actually able to answer that question that people have asked, you know, since cavemen first sort of looked up in the sky. And so that's the topic of this talk, is how are we actually going to do that in the next couple of years or the next few decades. So for years, right, the only planets we knew of were the solar system planets. And if you go back and you read a lot of the literature from the 80s and 90s about planet formation, there's a lot of discussion about possible formation scenarios that are very unique to the sun, right? That the sun may be the only star with major planets from it. We now know that that's not the case. Planet formation is common enough that it has to be a regular occurrence. And we know that because instead of just having solar system planets, here I've plotted them on a diagram of orbital size on the x-axis on the bottom, and then planet mass in Jupiter masses on the y-axis, right? So this is all the planets we knew of until about 1992. And then in 92, the first exoplanets were discovered around a pulsar, actually. So not even a star like the sun. The pulsar planets were discovered because a guy at Penn State, Alexander, I can never say it, he's got a very complicated, very consonant-heavy Polish last name, Walshans, which is embarrassing because I've actually been over to his house a bunch when I was a postdoc at Penn State, and I feel like I should get his last name these days, but I still can't get it. Anyway, they looked at a pulsar, they saw the pulsar. From the pulsar timing, they can see it moving very minutely. They discovered that there were a couple of actually sub-Earth sized planets. They found one that was the size of our moon orbiting this pulsar. And then in 1995, Mayor and Kalos found the first Jupiter mass planet around a sun-like star. And at that point in 95, the number of known planets just headed for the hills. And so we went from, we'll ignore the pulsar planets for a second because we're a little bit of an oddball. We went from 8 known planets in 95 to now 25 years later, we filled in this diagram. And we now have about 4,500 planets around 3,700 stars that we know of. And you can tell just from looking at this diagram, a couple of interesting things. Can you guys see my mouse? Is that coming through on the screen?
Yes, we can see it.
So one, there are a lot of Jupiter mass planets, much closer than Mercury. These are the hot Jupiters that were the first planets discovered. That was initially not thought to even be possible. Actually, once Mayor and Kalos discovered 51 Peg, the first 51 Pegasi, the first planet around a sun-like star, which is a hot Jupiter. It's got an orbital period of about 3 days. One, there was a lot of discussion about, is this even a planet? Could this even form? And two, a lot of other groups, particularly the group in California, finally looked in their data and they immediately discovered 5 of these things because nobody thought these could even exist. Actually, interestingly enough, this is a real sidebar. There was a very early radial velocity survey for planets by these 2 guys, Campbell and Walker. Walker was the grad student. Campbell was a professor still at the University of British Columbia. And they looked in the 1980s and they looked at 25 systems with the precision where they could have detected something. Statistically, when they look at 25 stars, they should have found something statistically, and they didn't see anything. And I met Campbell at a conference a few years ago. And we were talking at one of the, sort of the cocktail party at the beginning. And I said, do you guys ever feel bad about the fact that you didn't find anything? I phrased it better than that, right? But I asked him this, and he said, so one of the things that they used was to do, as part of their calibration, they used a bunch of heated uranium oxide. So they got uranium oxide, they heated it up and pressurized it so it was a gas, and they used that as a calibration source. But it's something where if that gas cell cracked, whoever was in the dome with the telescope had about a minute before they breathed this stuff in and breathed enough in where they got killed. So one of them, they'd switch off. One of them would be in a hazmat suit outside the dome, waiting in case this thing cracked. And if it cracked, his job was to pull his hood down, run in, drag the other one out. And that was their emergency plan. And so I'm talking to Campbell, 20 years after the fact at this cocktail party, and I'm asking him this. And he said, I got to be honest with you. We looked at 25 stars and neither of us died. I feel like we both came out of that feeling like we were successful. Okay, but so now we know about literally thousands of exoplanets around other stars. Many of them are Jupiter mass giant planets. Those are the easiest to detect for a variety of reasons, simply because they're much bigger than Earth. But we're starting to drill down into the region where we're getting down to Earth's closer to the star, and even some that are further out. Generally speaking, the bigger a planet is and the closer to the star it is, the easier it is to detect. So that's why there's a lot of stuff in this corner of the diagram. And then we sort of fall off as we move towards sort of where we're most interested, like around where Earth is on this diagram. Okay, most of these have been discovered by Kepler, which I wager most people have probably heard of at this point. Kepler is effectively a giant Schmidt camera that we launched into space. I don't have a picture of it, but if you can find a picture of the CCD array, because they had a whole bunch of detectors, 16 of them that they tiled into an array, and they have it at the prime focus, right? It's a Schmidt camera, and you can see the field curvature on it. It's a beautiful piece of engineering if you look at it. So Kepler found almost 3,000 planet candidates, many of which, and this is now in units of Earth radius on the y-axis and orbital period instead of physical separation, right? There are 3,000 candidates, many of which are about the size of the Earth. And a lot of these you'll notice were not on the plot that I just showed you, right? And the key difference here is these are planet candidates rather than confirmed planets. Reason being that something down here, right, like this guy who's the size of Mars and is about 10 days, Kepler can see it, but nobody else can. And so there's a lot of things that Kepler has seen that look like they're planets, but without independent confirmation, it's difficult to say. When I was in grad school, I sort of ran the operations of a transit search from the ground. And we probably had a hit rate of, we had about 100 candidates for every probably 2 actual confirmed planets that we discovered. It's better for Kepler, but it's important to remember for these candidates that there are a lot of things that go bump in the night, and not all of them are actually exoplanets. So that's the difference here. Kepler discovered these planets using a technique called planetary transits. So let's see if the video goes, right? So what Kepler was doing was it was looking at all these stars simultaneously in its field of view, and then it would look for, if the angle is right on a planetary orbit, we will see the planet pass in front of the star, its star, from our viewpoint on Earth. And when that happens, as it passes in front of the star, the brightness of the star goes down, the planet is obscuring part of the stellar surface, and so we get this dip in the brightness as a function of time. And for Jupiter passing in front of the star, passing in front of the sun, that's about a 1% effect. For Earth passing in front of the sun, it's 1/10,000th of a percent effect. So it's a much more difficult problem. Actually, interestingly enough, Jupiter passing in front of the sun, if you knew where to look, would have been detectable starting in like the 50s. We had the capability of detecting hot Jupiters. But again, nobody thought that a Jupiter-mass planet could exist on a 3-day orbit, so nobody went out and looked. If we had, we probably would have discovered the first exoplanet like in 1960, not in 1995. But the important thing here is this gives us a radius for the planet. We can estimate the radius for a star. We know how much area the planet is blocking, and so we can use that from the area ratios to get a radius for the planet. The way we get masses is by using the technique of radial velocities. This is a common one that people like to talk about. They call it the wobble method, right? Is you look at the star and the planet in a spectrograph, and the planet's moving around, but the star is moving around a little bit too, around their common center, on their center of mass. And for very large planets, this is a very exaggerated example. The star is moving quite significantly. It can move at, it can reach speeds of 100 or 200 or 300 meters per second over the course of the orbit. And so you look at the Doppler shift in the spectrum and you can measure that. So for Jupiter on a short orbit, you get about 100 meters per second. For Earth, on an Earth-like orbit around the sun, the signal is about 10 centimeters per second. 10 centimeters a second is, if I was standing in front of you, I could do a nice demonstration. It's a very slow walk. It's like if you were trying to like pretend you were slow-mo walking, that's about how fast you would be moving. So when people try and think about now measuring the masses of Earth mass planets, that's what they're trying to measure. They're trying to measure the velocity of a star to the speed, better than the speed of a very slow walk here on Earth. It's a very difficult problem. And when we think about life, what we're trying to do here, right? And so we get a radius from the transit, if we're lucky, if the angle's right, it passes in front of the star. We then, in principle, we can use radial velocity observations, the spectroscopy wobble method, to measure the mass. And so we now know, in principle, we can know the size of the planet, we can know the mass, and we can say, yes, this is an Earth radius, and this is an Earth mass. And then we look for things that are about the same distance from their star as Earth is, such that liquid water should exist, right? So they exist in the habitable zone of their star. The exact definition of the habitable zone right now is very fuzzy. A lot of people have a lot of different ideas about what this can be. To be perfectly honest, that's because we only have one example. Nobody has any other examples other than Earth. And so the theorists can have a field day defining the inner and outer edges of the habitable zone with only one example. And it's really going to be, once we actually start finding these things, everything's going to collapse down and we're actually going to figure out what's going on here. But generally we expect that, it should scale, roughly, roughly with temperature, right? If the star gets hotter, you should be further away from the star. As the star gets cooler, the habitable zone will move in and get closer to the star. So you put all this together, radius, mass, this idea of the habitable zone, and this has given us actually a whole bunch of potential habitable exoplanets that we know of. A couple of interesting ones just for nearby purposes are, there's a potentially habitable planet around Tau Ceti and around Capitan star. Both those are pretty close by. The rest of these, most of these are Kepler IDs because they don't really have a nice catalog ID, right? Tau Ceti is a name. Something like Kepler 296 has a telephone number that nobody can remember, so Kepler redesignates it. The GJ catalogs are moderately bright things, most of which are too faint to see. But we now have, probably 20 or 30 of these things that are nearby that we think might be habitable. Okay, and this is sort of the point of the talk, right? What we actually have when we say that, when we say we have a bunch of habitable planets, is we have a mass and we have a radius. Well, sometimes we have a mass. But we have a radius and we have a distance from the star. And from that we say, well, it's about Earth. It's about the same size as Earth. It's about the same distance from the star as Earth. So it should be about the same temperature. So therefore it's potentially habitable. The trick is, right, and this is what we see, right, in Kepler. This is what Earth would look like passing in front of the sun in Kepler. You get this little dip and it comes back up and that gives you a radius, but this is the information you have. The trick is that if you did this observation on the solar system, you would say that the solar system has two potentially habitable exoplanets, right? We have Earth, we have nice beaches, it's a nice place to vacation, it's a good place to visit. Another potentially habitable exoplanet that you would see in the solar system is Venus, right? Venus is almost the exact same mass and radius as Earth, it's almost the same distance from the sun, and Venus, melts anything we try and send down to its surface, right? So the question we can ask is, okay, once we've actually found, we have all these potentially habitable planets, how do we figure out if it's a place that has nice beaches and palm trees, or if it's going to melt our faces off if we actually try and step foot on it, right? And to do that, we have to actually investigate its atmosphere, figure out what's going on with its composition to try and estimate if it actually is sort of an Earth analog. Okay, so how would we do this? So the easiest way would be to image the planet. Just take a nice picture like this. We can see Earth has, you can see water, you can see land, you can see clouds, you can see vegetation, right? If we got an image like this of an exoplanet, you get the Nobel Prize, right? I think there are probably few ways to win at a science, but I'm pretty sure discovering other life in the universe would be one of the ways to win at astronomy. And you wouldn't even really need to do that resolution. If you got, 15 pixels across, you could sort of get the same information, right? The problem is that we can't get 15 pixels across. We can't resolve any of these planets. They're much too far away. We are never going to be able to actually resolve. Well, I don't want to say never, because there are insane ideas about building telescopes using, solar lensing that is the effective diameter of like 3 AU or something. But it's at the moment impossible to build a telescope that would resolve a planet around another star. We're only ever going to get one single pixel out of these things. And the other problem is that stars are very bright, and a planet like Earth is not very bright next to it. The Earth is about 10 billion times fainter than the sun. So you need to build an observatory that's going to be able to image something that's 10 billion times fainter than the star that's literally right next to it. The sort of conventional analogy that everybody uses is you're building, you're standing in New York City and you're trying to look at a firefly that's about 5 feet away from a searchlight that's in Los Angeles. And actually, I was actually sort of back of the enveloping that analogy just before we got on to make sure it still worked. It actually doesn't quite work. It actually really, that's actually significantly easier than the actual problem. The firefly and the searchlight are probably only different by about 100 million times. So the actual imaging and direct imaging of an Earth is about 100 times harder than that analogy would make you think. So it's a very difficult problem. That's not to say it's not solvable. There are actually, right now, there's a process called the decadal survey going on in astronomy, which is discussing, the astronomical community is discussing what it thinks the priorities should be for the next sort of 10 or 15 years. And it's effectively it's what, the community hands this report, the decadal, to NASA and to Congress. And effectively, that's how the money is budgeted. If the decadal says something is important and should happen, 9 times out of 10, Congress is going to fund it, NASA is going to fund it. That's how NASA sets its funding priorities, is by using the results of the decadal survey. One of the main things the decadal is debating is whether or not we should try and push for a space telescope that would be capable of doing direct imaging of an Earth-like planet around a nearby sun-like star. That is something that now is actually from space something that we could do. It's an engineering problem at the moment. It's not like a physics problem. We can do it. We just need to actually want to build this machine. If it gets selected, which it probably will, it's hard to see. The smart money's on the decadal recommending some sort of 6-meter direct imaging telescope that's going to do this with a coronagraph. If that gets selected, launch date maybe is 2040. So this is actually something that's being very seriously considered, and I think is probably going to be actually on the books starting in a year or two. Okay, but in the meantime, we can't do any of that. We need to find some other way of measuring atmospheres. So how else can we measure the atmospheres? Well, we can use the fact that for transiting planets, we have the planet going in front of the star. Here it's labeled primary eclipse. And we also have the planet going behind the star, here labeled secondary eclipse. The terminology, this is a super interesting diagram because the terminology here has been a real fight for the last, well, it was a fight for most of the 2000s. People got really annoyed that the terminology we've settled on is primary transit is when it goes in front, and secondary eclipse, which is like this bastardization of eclipsing binaries and planetary astronomy that satisfied nobody, but seemed to be what everybody settled on. Anyway, long story short, this diagram has a real agenda that is very amusing if you know some of the arguments in the past. Okay, so the planet goes in front of the star. What can we do with that? Well, you can imagine that as the planet goes in front of the star, for something that has an atmosphere, some of the starlight is going to pass through the atmosphere on its way to us, right? Most of the starlight hits the planetary surface, or it hits the very thick parts of, say Jupiter, and we don't see it. It just is completely blocked. But around the very edges, right? If you're looking at if you could actually see this planet going in front of the star, around the very edges, sort of a halo around the edge where the starlight is just grazing the top of the atmosphere. It would pass through the atmosphere, it would come out the other side, and it would keep going towards us. And that is what we want here. That's the sort of top panel here. As the starlight comes in and we're losing light, because what's going to happen is the starlight comes in, and then as it passes through the atmosphere, the components of the atmosphere, the oxygen and the hydrogen, the water and the carbon monoxide and everything, those are going to pick off photons at the wavelengths that correspond to, the absorption features of water and wavelength. right? Like water, if you looked in the infrared, has a giant absorption feature at like 1.4 microns. Specific number there is irrelevant, but just to say that if you took a spectrum and something had water in its atmosphere and you were looking at this, you'd see it would be, you'd be going along, and then as soon as you hit that water absorption feature, the water becomes opaque, all the light's blocked there, and you come back up, and so you can look for these spectra. The difficulty is that in the middle panel, if the gravity of the planet is very high, or for some reason the atmosphere is very condensed, let's say it was made out of just literally very heavy atoms, then the atmosphere is smaller, all the starlight goes through, you don't get anything. A more fiendish one is if there are clouds. If there are clouds, clouds are generally just opaque at everything. They block everything that comes at them. So if there are clouds, we also get effectively no signal. And, you know, all the gas giant planets in the solar system have clouds. The Earth has clouds. Even Mars has some clouds. Clouds are expected to be very prevalent in the universe. And indeed, most of the atmospheres that we've seen for smaller, cooler planets do seem to be cloudy. So this is an observation taken with the Hubble Space Telescope. And it's showing you, right, x-axis is wavelength, along here, and y-axis is, it's effectively the apparent size of the planet, right? So if the atmosphere obscures more, one way you can sort of think about it is the planet looks bigger, because you're now, instead of having that little halo of atmosphere around the edges be transparent, the atmosphere is opaque. That halo is now solid, and so the apparent size of the planet grows a little bit. And what they got was, they got a completely flat line here, which is a real classic signature of clouds. If there was no clouds, you would have gotten something like this red line, where here's one of those big water absorption features, and they come back down. This is a giant water feature here, and you come back down. But we've seen this a lot. We've seen these flat lines. That means they're clouds, which is interesting, but the problem is we can't really say what the clouds are made of, right? We just get a flat line. It could be a lot of things that give you that same answer. And it doesn't really tell you about what's going on underneath either. So this is one problem, is we're thinking about, how do we determine what the atmosphere is made out of? If everything's cloudy, it's going to be difficult to get underneath those clouds and see what's happening. So one way to approach this is use a technique called phase curve observations. So this is, you can sort of think of it like the phases of Venus, right? The planet on top here is going around the star, and it starts here in transit. We're seeing the night side, and then it rotates into view. The phase increases, it gets brighter, passes behind the star, it gets dimmer. And if you make a plot of the brightness of both the planet and the star, right? Because we can never pull them apart in these observations, is you get the transit, right? The planet is passing in front of the star. We're blocking light from the star, the brightness goes down a lot. Then we start seeing the day side of the planet come into view, the brightness goes up, planet passes behind the star, we lose that brightness, and then the day side rotates out and it comes back down. This is called a phase curve. And for short period planets that are a few days, this is something we can observe. Usually you have to observe these continuously, so there are a lot of telescope time to ask for, but you can do this. And these observations are very important because these are the only way we actually get longitudinal information, east-west information about what is happening in a planetary atmosphere. If you look at the transit observation, like what I was showing you here, that's telling you about what is the atmosphere sort of right at that edge halo, right at the terminator, sort of the combined dawn and dusk times of the planetary atmosphere. You can also look in eclipse, but that's just telling you what is happening across the entire day side. The only information we have about what is happening, you know, in the middle of the morning, what is happening in the late afternoon, what's happening in the middle of the night, comes from these phase curve observations by observing for an entire orbit. And so what we can get, see if this video goes, right? So this is a very nice observation from the Hubble Space Telescope from 2014, where they observed spectroscopically one of these, a planet called WASP-43 over the course of its orbit. So the interesting thing here for them is that there's this big water absorption feature right in the middle of these observations. And as it comes in, so this is in the morning, right? There's a lot of water. In the middle of the day, there's still water. And then in the afternoon, you start losing it. See how it goes completely flat? That's actually showing you chemical changes in the atmosphere over the course of a day on this planet. That the hot atmosphere that's present, or the cooler atmosphere that's present during the morning has a lot of water in it. And then as it heats up across the day side, you lose the water. You know, it either moves elsewhere in the atmosphere or, you know, something happens to it. It sort of disappears. And then it comes back on the night side. You can't really see the night side here, but it has to come back because you see it the next morning. So this is, what this means is this is a way we can, one, get around clouds because we can look for these spectral changes over the course of the orbit. And it also tells us something about the chemistry, you know, what's happening on the day and night sides of these planets and, you know, how does that change? For a planet like the Earth, the day and the night side chemistry of our atmosphere doesn't change that much because we're effectively sort of the same temperature day and night side. What we're looking at here is a very hot planet. The day side is about 1500 Celsius and the night is about 800 Celsius. So there are large chemistry changes happening in this instance. Another thing we can do is we can use those chemistry changes to try and map clouds. This is actually an observation that I took using the Hubble, the Hubble Space Telescope, where we looked at that water feature at 1.4 microns. And when it's not there, our conclusion was this planet should have water on it. We should be seeing this. When we don't see that water feature, that means that we're being obscured by clouds. They're blocking our view lower into the atmosphere. And then as it comes in, those are the clouds sort of coming off. And so what's happening is there are night side clouds on this planet. They're not really shown here. That form on the night side, and then they get blown onto the day side. And by afternoon, they're heated up enough that they've all disintegrated. And so it's this dynamic process of cloud formation on the night side, and then these winds that are hundreds of meters per second strong blow them onto the day side. The day side is way too hot for the clouds to exist. And so over the course of a couple hours, they spread across the day side and then just disintegrate until you get into the afternoon where things are so hot that nothing exists. And then as soon as the sun sets, you get the cloud formation coming back in. Which is all to say that these are very, you know, often when people talk about exoplanet atmospheres, they sort of have one idea of what's going on, but these objects are really not, they're not cue balls in space where, you know, they're these sort of featureless things we look at once and we get. There are these dynamic objects that have these clouds happening that are blowing across the day side. You know, this is even for the hottest planets where we think most of this is simplified. You know, as we get towards planets like Earth, these atmospheric dynamics are going to get much more complicated. And one of the things we're going to have to address that I think not many people are thinking about is if we look at an exoplanet once, right? These observations are very time intensive, right? We got one set of Hubble observations to look at this planet. If we came back a month later, would we still see the same thing? Like, how much is what we're seeing just the weather on the day that we observe versus the overall climate of the planet? That's something that I think people are just starting to think about. I actually have a grad student working on an observational project that's just on this topic, right? We got 3 repeat observations of an exoplanet, took its phase curve that are, you know, a couple months apart to see if it changes, because nobody's ever actually done that experiment before. Let's just look at one of these things multiple times and see if we get a different answer at different times. You know, is there weather present on one of these exoplanets? So that's going to be a fun thing to investigate as we go forward and as we get better data where we can probably see this effect even in more detail. Okay, but so far we have mostly big hot planets. What we really want is things like the Earth. And let's say we can. Let's say with JWST, with next generation space telescopes, we start looking really in detail at the atmosphere of these planets like Earth. How do we actually tell if there's life present? What would we look for in the atmosphere to tell us if there was life on another planet like the Earth? So as probably you can guess from the structure of the talk, the main thing we look for is what's in the atmosphere, right? We look for things like methane, we look for water, and we would look for oxygen, right? Oxygen is, it sounds simple, but oxygen is a really important biomarker on the Earth. So right now, about 20% of Earth's atmosphere is oxygen. If there was no life on Earth, the oxygen content in our atmosphere would be about 0.5%, right? We would have effectively zero oxygen in our atmosphere if there was no life on Earth. The only reason oxygen exists in quantity in Earth's atmosphere is because life is present and it's producing it through photosynthesis. So that is one of the primary biomarkers we look for. Is we look for oxygen. We look for water features, right? This is an example of here the sort of spectra, right? The sort of amount of light you get off a planet as a function of wavelength. And you can use that to identify chemical species. So something like Mars doesn't have a lot going on. It's got a lot of CO2. But Mars, there's no water here. There's no oxygen. You could tell that looking at its spectra. Venus actually also doesn't have, it has some water, but it has a lot of CO2, but also no oxygen, no ozone. And Earth has this giant ozone feature right here. There's a lot of water all over the place here. It's really bringing you down over here. Still some CO2, and there's lots of oxygen features out here. So ideally, what you would see is if you looked at one of these spectra, is you would see oxygen, you'd see water, you'd see some CO2, some trace gases. And that would really be a very strong indication. I don't want to say a slam dunk because there are some geologic processes that can, cause oxygen to be present. But if you had, oxygen, water, reasonable amount of CO2, and I haven't mentioned methane. If you had a reasonable amount of methane, about Earth's level, all four of those, if you measured all four of those and you could see that they were like Earth, then you could be, I think, extremely confident that there was some biological process producing this. Generally, the idea is that we want something for a biomarker that is very reactive. Something like oxygen is perfect here because oxygen loves to rust things. It loves to come out of the atmosphere in any way it can. Like I said, the only reason why oxygen is present in Earth's atmosphere is because life is here and is constantly producing it. Otherwise, it would just rust out or whatever. It would come out very quickly. So it may be possible, barely, to see some of this with upcoming space missions. So this is a simulation for the James Webb Space Telescope of, whoops, I keep brushing my mouse and my scroll wheel jumps us forward a couple slides. Right, so James Webb barely will be able to see this. This is for, I think this is actually for the planets around TRAPPIST, which you guys may have heard of. It's a very nice system, but it's something that you would need to spend 28 hours worth of time to be able to, this is a real marginal detection actually. So you'd have to spend a lot of time to get something that's pretty marginal to be able to do this. But for some very specific exoplanet systems, we may be able to do this with James Webb. Another thing you can look for if you have better imaging is you can look for something called the red edge. So vegetation on Earth, like trees, leaves, grass, everything that uses chlorophyll, actually has a very distinct spectrum where if you looked in the infrared, so this is an optical image, everything looks green over here. And then over here is sort of a simulated infrared image where you can see it suddenly gets bright red everywhere there's vegetation. The reason is that plants spend most of their time trying to prevent themselves from overheating in sunlight. So they want to absorb all of the sort of yellow light to run photosynthesis, but then they want to reflect everything back out, like all the infrared light, so that they don't overheat. So plants actually look extremely red if you were looking in the IR, right? So here's wavelength, optical, sort of what we see, visible light is over here. Plants absorb almost all of that through chlorophyll. And then as soon as you start moving into the infrared at longer wavelengths, they reflect almost everything that comes onto them. And so what this means is that planets are very reflective in the infrared and have a very specific, because of chlorophyll, reflectance signature here. So if we were looking, and this is actually what a lot of the like the Landsat satellites use to look for like forest cover and sort of agricultural imaging, is they look for this red edge to judge vegetation extent. So if one thing we would look for vegetation specifically, and that uses chlorophyll, would be something like this red edge, this sharp reflectance signature that occurs as you move into the infrared. Another thing you can take advantage of is the fact that oceans and land actually reflect light differently back at you. So if you were looking at the Earth, you could use this difference in the reflection spectrum from ocean and land. And you could actually probably crudely reconstruct the Earth's landmass, right? So this is, what you do is you look over the course of a day as the Earth, different parts of the Earth rotated in and out of view. And so you wouldn't get any latitudinal information. So down here is the reconstruction, right? There's no latitudinal information. All you have is an east to west measurement, right? But you can, from looking at this, you could recover, right? Africa and Europe, there's a lot of land here. There's a lot of land over where Asia is. There's probably an ocean right here. And then here are the Americas over here. You could look at these different reflectance spectra over the course of a day as this planet rotated, your single pixel, remember, and try and look for this. The one actually amusingly, well, not really amusingly, but maybe, well, amusing or frustrating, depending upon how you want to look at it. Problem with this is that if you didn't know the moon was there, you wouldn't actually get, what you'd think is that Earth had a 28-day rotation period and there was land all on one side and there was no land on the other side of the Earth. So if we didn't know the moon was there, this technique doesn't work. So I don't think anybody has a solution to that at the moment. That's going to be a fun thing to figure out, because if we actually get something and we try and do this experiment, how do we figure out if we're actually recovering the actual land masses, or this thing just has a moon at some arbitrary orbital period orbiting it? Another thing you could think of looking for is actually just look for evidence of technology. So pretty much all of the current next generation space missions that would be able to do this, that would be able to look for biomarkers, biosignatures on other planets. Their design has effectively been driven by the desire to look for biosignatures. You know, you say, we're going to go try and find life on an Earth-like planet, and we're going to design a telescope capable of doing that. What does that mean? We're probably going to look for oxygen. We're going to look for the red edge. We're going to look for these classic biosignatures. And that's what we're going to baseline our telescope to be able to do. Those designs are very capable of looking at exoplanets. And what that means is that we can not only think of looking at biosignatures, but we can start thinking about looking for what people are starting to call technosignatures, right? We're definitely going to look for biological signs of life. We can also start thinking about, because we're going to have the capability to just barely do this, to look for technological signs of life as well. So traditionally, the way this has been done, right, is you know, sort of the classic SETI model of, we're going to look for active radio or optical emissions, that they're beaming us radios, they're using lasers to communicate with us. One of the problems with that is it can be sometimes difficult to know what you're seeing. So this is, if anybody knows the SETI literature, this is the printout of the WOW signal that was detected actually by a radio telescope at Ohio State, where suddenly they got this sharp pulse of radio energy, and I forget what they were looking at. But the problem is they got one sharp pulse, and it sure looked like, you know, some sort of like search radar, but maybe it was a pulse from an alien, you know, civilization that we just happened to pass into. But it was difficult to know where exactly in the sky they were pointed, because radio is sort of coarse angular resolution. And in principle, it could have just been the Air Force, you know, flying overhead for a split second. That's what they picked up. That's not to say, but, you know, radio SETI, I will say, has given us one very clear result. I think it's interesting to remember that, everybody thinks of, I think, SETI is a success if it detects radio signals from another civilization. I would also say that SETI has been a success because it hasn't detected any radio signals from another civilization. Because there's a scenario here, right, where you start looking with the radio telescope in the 60s when they first started running radio SETI surveys. And you look at Tau SETI and you look at Alpha Centauri and you look at Epsilon Eridani, and you just immediately hit the big time, right? It turns out we are surrounded by civilizations like us that are broadcasting at radio, and we pick it up immediately because we could do that in the 60s, and it's off to the races. So SETI actually has given us an answer, right? That scenario that I just described to you, where we're surrounded by other technological civilizations that are like us around nearby stars, isn't the case. We would have seen it if that was happening. I think that's not the answer any of us wanted. And that's why it feels like SETI has been unsuccessful, but in many of the ways, like SETI has given us an answer. It's just, I think, not an answer any of us wanted when we started doing it. Okay, but right, we have these giant telescopes. Maybe this isn't going to happen, but one of the things the Decadal is debating is putting a 16-meter space telescope up into orbit. That's never going to get built, but in principle, it could. Once we do that, or even if we have the 6 or 8 meter version, what can we actually do with the planets themselves? Well, one thing you could do is, could we see industrial pollution, right? We're doing all this work to characterize the atmospheres. We are modifying the atmosphere on Earth. Could we see industrial pollution on another planet? And actually, this image pretty well illustrates the difficulty in doing that, which is most industrial pollution and smog stays pretty close to the ground. It doesn't propagate upward into the atmosphere. And what we want is something that gets high up in the atmosphere that's easy to see. If it's this smog layer, clustered around the LA Valley, we're never going to be able to see that in these sorts of observations. But people have worked out, what sort of could you see? The main things would be nitrous oxides, methane, CFCs. The nitrous oxides and methane have they're a bunch of natural sources, so it wouldn't really be a smoking gun if you saw those. CFCs, though, if you saw those in a exoplanet atmosphere, because those can get very high up in the atmosphere, those are very likely to be artificial. They last for a long time. That would be a very good sort of smoking gun for, there's an industrial society that's pumping out smog into their atmosphere. The problem is that for a planet like Earth, the place where you would look for CFCs in the atmosphere has a lot of other stuff present. It's very difficult to see the spectral signatures of CFCs at anything close to the current concentrations. So unless they would have to be at least 10 times greater than what's currently present on Earth for us to be able to detect them on an exoplanet. What that probably means is that if we could detect them, if we could detect industrial pollution on an exoplanet, it wouldn't really be like Earth. It would probably be some sort of post-industrial wasteland that would not necessarily be a great place to visit. It actually would probably be the most depressing resolution to SETI is we found another civilization, but they've managed to kill themselves before we got there. One thing that I've actually been working on is the question of are night side city lights detectable? Right, we're going to image these planets in really a lot of detail. Could we also image them at night and try and detect city lights from them? So the idea here is that the lamps we use on Earth actually have very distinct and concentrated emission features. In particular, the sodium lamps that are most streetlights, though a lot of them have started being replaced by LEDs. But sodium lamps in particular have very concentrated emission. And there's nothing on an Earth-like planet that gives you, you're not going to get high pressure sodium electrified, into a neon state on a naturally occurring on an Earth-like planet. So it's a very distinct signature to look for. Right, it's very concentrated, so you don't have to look very far. You know exactly where you're looking to. And actually, for some of the larger space telescopes, like the 16-meter one I mentioned, if you were looking at some of the nearby planets, like Proxima Centauri is a potentially habitable Earth-like planet around it. If you were looking at Proxima Centauri, you would be able to detect the city lights from, not Earth. Earth is impossible, but if Earth had 10 times more cities, we would be able to detect that around Proxima Centauri, around its planet, and be able to identify the fact that there were cities and a technological civilization present on the surface of Proxima Centauri b. Okay, so I will end with this picture again, right? I started with the idea that, you know, astronomy's been around for thousands of years, and we've been thinking about this question, you know, are there planets like Earth up there? Are there, you know, early on, is there other humans, but, you know, just as there other life out there for thousands or hundreds of years? And really, you know, the work that we are doing right now is built on that thousands of years, hundreds of years worth of work, right? Like day to day, I use, you know, the magnitude system, which was worked out by Hipparchus in like 500 BC, right? I day to day use a 2,500-year-old system for describing the brightnesses of stars. You know, the stuff that we are doing today is the very tip of a tower that has been built for us by scientists stretching back for hundreds of years. And the very exciting thing is that we are close. We are very close. We can do this. We just need to want to do it. We just need to get the funding, and we need to build these machines. And we can actually answer these questions in the next 10 to 20 years. We can put up an 8-meter space telescope. We can build the instruments that are able to image planets like Earth. That's just an engineering problem at the moment. It's not a physics problem. If we get the money, we can build these machines, we can put them in orbit, and we can actually image these things. And we will have a much better idea. Hopefully we'll actually find something, and we'll actually be able to answer the question for the first time in 2,500 years of whether or not we're alone in the universe. And I was just talking about that, about, you know, my day to day, but I mean, I really mean this in terms of like everybody, right? Like each of you who are listening to me right now, right? There is a real high probability that in our lifetimes, we will detect life on another planet based on what we know about exoplanets, their prevalence, and our ability to build these observatories. And to me, that is a tremendously exciting moment to exist in. That we get to be the first ones in the history of the world to know the answer to the question, are we alone in the universe? And hopefully that answer is no. Hopefully the answer is that no, we actually find life elsewhere and we're no longer alone. Hopefully that's the outcome here. But either way, it's a very exciting time to be involved in the field. And it's also why I really enjoy talking about this to people, and particularly astronomy clubs like you guys who sort of get it. So thank you very much for listening, and I'll stop sharing and I'll take questions.
Great. Thank you very much, Dr. Beatty. If anyone would like to ask a question, be sure and unmute yourself. We're not able to unmute everyone. Or you can put your question in the chat, and I think, Bob, you usually handle that if you don't mind.
Don't mind.
I just want to say thank you very much. That was interesting.
You're welcome.
I heard.
It's always nice to get a captive audience to just talk their ear off about what I do day to day.
It's pretty. I'm sorry. Go ahead.
I have a question.
Sure.
It seems to me from things I've read that looking for radio signals, typically in the 1 to 10 gigahertz band, that would indicate transmissions from other civilizations, is not understood very well. What I mean is, even SETI has on their website that under optimistic assumptions about other civilizations, assuming they were at about the same level of technology that we are, at best, we might detect radio signals from 1 or 2 or 300 light years away, and that's at best. Mostly looking at high-powered military radar signals that are fairly directional. so they don't fall off so fast with distance. If you look at what people do with the Drake equation, they usually start with the number of stars in the whole galaxy and how many of them have planets and blah, blah, blah. But the great majority of those stars are apparently far outside of our radio detection range. So if that's the case, then we may only be sensitive for the most part, according to the SETI website, to maybe tens of light years detection distance for radio signals. If that's the case, then we've been amiss in our estimations of what to put into the Drake equation. On the other hand, that says there could be civilizations just a few tens of light years away from us actively transmitting, and we just can't detect them because they're lost in radio noise. Optical SETI probably has a significantly longer detection range, but it's much more directional. So if somebody isn't pointing a laser beam pretty much awfully close to right at us, we wouldn't be able to detect it. So those comments I just made may be controversial, but that's what I'm seeing. Do you have any comments?
Yeah, I think, well, I think they're probably not too controversial, actually. I think the radio and the optical SETI guys are very aware of this. And I mean, I think that's exactly right. That, well, let me say that I think whatever we do, whatever method we choose to approach the problem of looking for technosignatures and trying to find, you know, technological life or even biological life, there is going to be some detection horizon, right? We're only going to be able to do it out to a certain distance using whatever techniques we're using. And it's going to be, it is going to be a real bummer if it turns out that, you know, with the current generation or even next generation instruments, that detection horizon is, let's say it's 100 light years using whatever method you want. If there's somebody at 105 that we're just barely not getting, and we discover that 80 years from now. But one way to look at that in the case of, we'll say, non-detections, if we get up there and we see nothing because everybody's just outside of our horizon, is we still can learn something from that. That still gives us the, you know, an upper bound, right? Think about the Drake equation. If we didn't see anything, that would give us, and even classic SETI now has given us some upper bound on what the values of those numbers have to be. Because if they were much higher than that, you know, we'd have a civilization at Alpha Centauri that statistically that we would have seen. So even if we don't see anything, you know, these missions will give us constraints on the prevalence of life and of technology in the galaxy, which, again, I think everybody wants us to get a hit on these missions, but if we don't get anything and we just get these constraints, that is going to give us useful information about, you know, the evolution of life and how that proceeds, because it probably means it's a little bit harder to do than some of the more optimistic estimates.
I guess I do have another comment. In our own solar system, Mars, apparently, according to what's been learned from the Curiosity rover, at one time had a habitable environment quite a long time ago. And I think it's pretty likely that on a reasonable time scale, we're going to have evidence one way or the other whether there was ever life on Mars. I don't think, well, I think the Curiosity and Perseverance rovers have limited capabilities to look for it because they can only drill a few inches into the ground there. That's likely not deep enough because the environment at the surface is extremely hostile to life with ultraviolet light, cosmic rays, and perchlorate toxic compounds.
Yeah.
But if the next generation of rovers goes deeper, which I hope it does, we may get an answer. And that answer should be positive if it's true that whenever on any exoplanet there's a habitable environment for a reasonable length of time, life occurs.
Yeah, so that's a very good point. The idea of the time evolution of habitability is something that a lot of people are thinking about. Like Earth throughout its history has looked very different. 500 million years ago, the atmosphere of Earth was very different from what it looks like today, but there was still life on Earth. And so one of the things I think we have to look for when we go out and do these observations is, I didn't have time to go into it, but yeah, people will be looking for, the popular thing is the Archean Earth, like what was the Earth 500 million years ago? You could look for atmospheric signatures like that, and that would be a planet that has life on it, but isn't really Earth-like. The general idea of time evolution of habitability sort of goes back to my sort of side comment about the idea of the habitable zone. My sense is that there's a lot of theory on this about what can work and what can't work, that exists because we have one example on Earth, and that if we actually go out there and we find a couple of planets with life on them at different points in their evolution, that all these theories are going to collapse down because everybody's going to be like, oh, it turns out that's what was important the whole time. It wasn't any of the rest of this. It's you need X, Y, and Z, and ABC isn't actually relevant. But that general idea that habitability changes over hundreds of millions of year timescales is something that people are thinking about a lot.
I have one other comment or question, if I'm not using up my quota here. Your talk has centered on looking for life on planets. Based on that, one would not expect there to be a possibility of life on places like Jupiter and Saturn, but their moons, Europa, Enceladus, and maybe a couple other Galilean moons may have underground liquid water or under ice liquid water. My assumption, correct me, from what you've been saying is that's going to be even tougher to look for than the kind of studies you've been talking about doing on planets. Yeah,
I think certainly something like looking at life in Enceladus is under surface oceans. I can't imagine that would be possible to do unless you went there. But I will say the general idea, right? Titan might be doable though, because that has a significant atmosphere. If we saw something like Titan, and that also is something that I didn't have time to go into, but people are thinking about, what could we do with large moons to giant planets? I will say generally though that, a lot of this is, in principle, there can be a lot of forms of life out there that are not like Earth. And I think everybody has in the back of their heads that we have to try and keep an open mind. We gotta, this could pop up in a way we don't expect. But if you have to design a mission, and by that I mean you have to go to Congress and you gotta ask for money to build one of these things, you gotta start with some baseline design. And for us, the obvious baseline design is we're gonna go try and find a planet like Earth around a star like the sun, because we know that works. Now, Is that the only thing that's going to work? I hope not. I hope that there's, floaters and giant planets, atmospheres, that there's, methane life on other Titans. There's all sorts of stuff. But as the sort of baseline design for all this, the assumption is the first thing we're going to go look for is something like life on Earth. I think, Sandra, you had a question in the chat. Do you want me to share my screen again?
Yeah, I have a couple of questions about some of the charts. Some of them are quick questions.
Sure.
One is a chart that said Kepler found almost 3,000 planet candidates. And then there's like a scatter chart. And in the legend, it shows like 1, 2, 3, 4. Is that the number of planets in the solar system, in the system? Or what does that mean in the legend?
Yeah, that is exactly what that means. So there's.
Okay, yeah, that was a quick question.
Right.
Then the next question is a chart that shows the potentially habitable exoplanets. And there's a whole bunch of little planets there. It's titled, "This has given us several potential habitable planets." And some of them have a little, it looks like there's an asterisk after the name, but I can't see the asterisk, what that asterisk is supposed to mean.
Oh, so that means that those are they're planet candidates, which generally means we have a radius for them and we have an orbital period, but we don't have a mass. So something like Tau Ceti E, right? That has an asterisk.
Yeah.
That has a radius, I think, of about 1.5 Earth radii, but in principle, that could be 1.5 Earth masses, or it could be 5. And if it's 5, it's very different from. It's probably not solid. It's not a terrestrial planet like Earth. So the asterisks just mean we don't have masses. We only have radii.
Okay, and then the final question is, I didn't really get, there was one about that's titled, "We can use phase curves to map the clouds," and it's got these bright dark blue and pink and yellow and white colors. And I don't see a legend for what it seemed like you were saying the dark blue meant there was clouds there, but I didn't follow that 100%.
Yes. So I can admit I stole this from one of my papers, where in the paper it has a very long caption that explains what's going on. So yes, so the color coding here is the light sort of white color is no clouds, and then the dark blue is more clouds, and the intermediate sort of purplish colors are some, partial cloud cover or something like that.
Great, thank you so much. Those were all my questions. And I just also wanted to say that that was a really great talk. Thank you so much. I've always been interested in exoplanets, and I've seen a lot of presentations. It's like, okay, that's the same thing I've heard before, but I learned a lot of new things in this presentation. So thank you so much.
Thanks.
No more general questions on the chat at this time. Anybody would just want to pipe in, turn on their mic, and go ahead and just ask.
I have a question. When you're looking at transiting planets, and like our solar system has, like lots of planets circling around it, does that cause a problem when you're looking at where multiple planets are transiting when you're observing those?
So I'm trying to think. So usually, if you get multiple planets, everybody gets excited because it's sort of like a 2 or 3 for 1, or in our case, 8 for 1 sort of deal. In some cases, it has been confusing because you see a transit event and then you see another one, and it's sometimes, if the planets are very close to the same radius, it can be hard to figure out, is this the same planet or is it a different one? If we were looking at the solar system, everything has a different enough radius that I think we'd be able to pull it apart. The only tricky one would maybe be Earth and Venus, but I think those are different enough that we'd be able to distinguish them as well.
Thank you.
Anyone else? I've been really impressed with all the facets of the exploration that's going on. Yeah. So thank you for that.
I'll ask a question, Bob, if you don't mind. I did read a year or two ago, I don't remember who the astronomer was, but he was wondering that the universe is so old now that maybe all the life is gone. Maybe we're the last of the life in the solar system. Do you agree with that? Do you think that's a possibility?
So I guess, I mean, is it a possibility that we're the only life that exists in the universe? I mean, we have to, I think, confront the possibility that that's the case, because we haven't seen any evidence for other life, but we haven't, at the same time, we haven't looked very hard. You know, some examples people use is that if you randomly landed a lander on Earth, if you were doing a mission to Earth, if you were an alien, and you landed in the middle of the Saharan desert, and you just looked at one very small part of the Earth, you get a very different idea of what it looks like than everywhere. So we haven't looked very hard, but I think we do have to confront that possibility, even if it's probably not the idea we want. I can't help feeling that that is unlikely. My own personal opinion, which is based on no, I'm going to say this is not based on science, this is just my own personal opinion, is that I find it hard to believe that we're the only life in the universe. And I think it's very likely that, once these next gen telescopes, this 8 meter, the coronagraph gets launched in 2040 ish, I would be extremely surprised if they don't get something in a couple of years, actually find life on another planet. But that's just based on my
different
own
question, though, isn't it? Then I think I forgot who asked that question, but I think many people, or certainly I believe, that we couldn't possibly be the only life. But the question was, given the age of the universe, maybe there was a lot of life and it's already died out by now, and we're just the last ones left. And I find that unlikely as well, too. But what do you think about that?
Right. Well, so I guess, right, for specifically the age, I guess, I mean, to me, the longer the universe goes on, even if life is some improbable event, the longer it goes on, the more times you roll the dice, and the more times you get a chance to, roll snake eyes or whatever you want it to be. I will say, interestingly enough, people have worked out that in principle, there could have been another civilization on Earth. Like if there was a civilization that existed 400 million years ago, there would be no way to know. If they came and went over the span of 100,000 years, 400 million years ago, it would have all been washed away by this point.
That was the one thing I was going to bring up, is our actual species lifespan is so tiny compared to the universe timescale that life that has the intelligence, at least at the level we are, and the technology that we've only acquired in the last 100 years could have happened billions of times through the universe, and still could happen billions of times through the universe, because our lifespan as a species is so tiny, it's kind of irrelevant to even ask that question.
Right. I will say though, there's sort of an optimistic and a pessimistic way to view this, which is that an intelligent civilization, the pessimistic way is, they're just going to blow themselves up or, poison the atmosphere after a certain amount of time. The optimistic way to view it is that, I heard this once in a talk, that the primary difference between us and the dinosaurs is that we have a space program, right? The dinosaurs got killed by an asteroid. If we saw an asteroid coming and we had 30 years worth of warning, we could do something about it. The dinosaurs could not. So an optimistic take could be that, once you get intelligent, that you start being able to prevent the natural extinction cycles occurring to your species, and that you can keep going for a very extended period of time.
So
or we might just blow ourselves up though.
And it's certainly true that there's many stars being born all the time, and they're getting solar systems. And so to say that the universe is so old that all the life could have been died out, there's always new planet systems being formed.
Right. Yeah. It's a lot of rolls of the dice, even if
And even your search for even the search that we have been doing for 50, 100 years, whatever, is a very small time slice, and assumes that that the transition of the technology we're looking for is in the same time domain as we are. I mean, that's a very very a small slice of time.
Right. Yeah, that would be a real bummer outcome if it turns out there were other intelligent civilizations, but they've all just died off, and we can somehow figure that out. And we just missed them by 50,000 years or something.
I mean, if I can comment on that, if you look at stellar populations in the Milky Way, there's nothing that says the Earth is on the tail end of producing sun-like stars in our galaxy. They continued to be created for a long time after our sun formed. And if some of them wound up with Earth-like planets orbiting around them, and they started it, after we did, if evolution took about the same length of time to produce intelligence, I mean, there would still be new civilizations coming along every so often in our galaxy. I can't see any rationale for thinking that if there are many civilizations, that we would be the last.
Right. So
Yeah, that's what I was trying to say. I agree with you, Dale.
Yeah. I was going to say one thing I really like about the character of this discussion is that it's very similar to some of the discussions we have at conferences about habitability and stuff. It's really emblematic of, we only have one example, which is us, and there's a lot of different ways to go. And one of the exciting things coming up is that if we start getting hits, we start getting nothing, that's going to really collapse, the possible theorizing. So all of you, if you ever wanted to go into like habitability theory, go for it. It is a great time to get into it because nobody can prove you wrong at the moment.
If we only had the time.
Right.
Yeah, I was just trying to, point out the variable of time that's really important in this equation.
Right. Yeah. Unfortunately, there's always a problem with astronomy is we never actually get to. Time is such a large part of this, and we just get such a small segment, But that being said, right, stars live for 10 billion years, but we've reconstructed a stellar life cycle. The analogy that I always use is it's like you're walking through a forest, and you're never going to be able, well, you could, I guess, sit there and watch a tree grow from a seed into a full tree and then die. But if you walk through a forest, you could look around and you could see, seeds, you could see saplings, you could see giant trees, and that's sort of what we do with stars is we just look around, we see things at different times and we reconstruct from that. So hopefully we can do the same thing with life and civilizations if we get enough examples.
I think too that even if we didn't find intelligent life, I mean, if we found a planet that just had only plant life on it, it would be super exciting. I mean, if you
or
could tell by the
bacteria.
oxygen and that kind of thing, just to find any life, intelligent or not, would be super exciting.
Yeah.
I have a question about Titan, Dr. Beatty. You mentioned, it has a thick atmosphere. It's a totally different chemistry than the Earth. Maybe there could be a different kind of life there. When I think about that possibility, the problem that comes to my mind is the temperature there. It's roughly the temperature of liquid nitrogen on the surface. And there's a rough rule of thumb in chemistry that I remember from way back, which is that the rate of chemical reactions roughly doubles every time you increase the temperature by 10 degrees Celsius. If you work that backwards to the temperature on the surface of Titan, you're talking about chemistry slowing down by a factor of roughly 1 million. So are there people who seriously think there could be living things on the surface of Titan in view of that issue?
That's a very good point. So I'll admit I'm not very well versed in what the most up-to-date thinking is. My vague sense though is that Titan is just, it's got so many of the right, it's got all this organic gunk on it, that if you wanted to look anywhere for, and it's got this methane hydrological cycle that if you wanted to try and come up with some crazy low temperature life, that maybe you could get it to work because it's got organics, it's got some sort of hydrological is not the right word, but because it's methane, but hydrological cycle. But I think that point though, that whatever's happening would have to run real slow, and that complicates things, I think is very on point. But I'm not familiar enough with the topic to really say more than that about it.
Okay,
Yes,
thank you.
there's a lot of DNA components, when you said that organic gunk, they actually have all the components to make DNA that they've discovered already on Titan.
Can't wait until we get a probe that lands there and does more research.
Well, if you joined late, our October 23rd presentation is going to be about landing a helicopter on Titan. So Dale, you want to mark that down.
Okay,
Called Dragonfly.
Yep,
right.
exactly. Yep.
Do we have any more questions for Dr. Beatty?
Been a great
Right.
presentation. Thank you
Yep,
very much.
it was wonderful, Doctor.
Yeah,
Thank you very
yep.
much.
Thank you.
Yeah,
thank you,
Thank you very
guys.
much, Dr. Beatty.
Very well done. Thanks a lot.
Yep, it was a
Thank you
pleasure.
very much.
So that'll be the end of our meeting technically.